All right, so now we know how to get air to go into and out of the lungs. And we've talked about that Boyle's law that talks about the relationship of volume to pressure. And obviously a pressure gradient moves the air. And again, pressure gradients work in a very similar way to concentration gradients. Right? If I have two tubes that I want to move air through, and I have a ball on this side that has air at 100 millimeters of mercury, and I have air here that is at 50 millimeters of mercury, through which tube does the air move faster?
You don't know.
Exactly, you don't know. See, I love it how you guys caught on to all my games. Right, because we have no idea what's going on this side. What if over here it's 90 millimeters of mercury, and over here it's 5 millimeters of mercury? Which one's moving faster now? B, right? So pressure gradient moves the air, and the greater the pressure gradient, the faster the movement of the air. Or what we can refer to as the flow. So the flow of the air is again going to be directly proportional, and let's cheat. Is directly proportional to the pressure gradient. So again, I've changed the number, but still, which one is going to move faster, A or B? B. How much faster? Twice as fast, exactly. Because notice here the difference is what?
10,
Here the difference here is
20.
20. So notice basically we have doubled the pressure gradient, so we have doubled the flow. So just a fancy way of saying the greater the pressure gradient, the faster the air is going to move. However, there is another factor that affects the flow of our air, and that is resistance. I need a teeny bit more room, so I'm going to cheat. So resistance and flow are inversely proportional. Resistance is essentially the friction or the force that must be overcome. Let's set up our two tubes again. And again, we'll put 50 on one side, and we'll put 10 on the other side. So the pressure gradient is the same. But in one of them, we're going to have a 2-inch diameter tubing, and in the other one, I'm going to have, and again, these numbers not realistic, but I'm going to do it anyway, a 1-inch diameter tubing. Which one is going to have the more rapid flow here, A or B? A, exactly. Right? Basically, what we have here with this larger diameter is we have a smaller surface to volume ratio. Whereas with the smaller diameter, we have a larger surface to volume ratio. And basically where gases get friction is when they make contact. Friction is basically when the air makes contact with the walls. Right? It slows it down. Right? That's why ice skates are super tiny and thin. Right? In fact, if you've ever looked at an ice skate, right, those blades look really impressive because they have that tiny blade on the bottom. Does anybody know anything about ice skates? Is that entire ice skate a blade in contact with the ice? No. If you actually look at the underside of it, it's actually concave. You actually just have two tiny little surfaces that are in contact with that ice. So very little contact with the surface, very little friction, and you can easily glide against the ice. Here, much more of the air is bumping into the walls. We're getting more friction, and it slows it down. And since our diameter has halved, what would happen to my resistance?
2 times as great.
Yeah, double, right? Because it's inversely. So if the resistance has doubled, then our flow is going to be cut in half. All right? And we can put them all back into a nice equation like that, or we can keep them separate to keep them thinking that way. All right? So when we're talking about the air, movement of air, we have to talk about the pressure gradients, we have to talk about the resistances. Questions on that? So when we look at the basically resistance and the flow of air as it moves through, not surprisingly, when we get down to the terminal bronchioles, there's almost no resistance because they're so tiny. Wait, wouldn't that mean there's a lot of contact with the walls? Why is the pressure so low in the bronchial terminals, terminal bronchioles? Say again? No, not a bad guess. I like that. That is a good thought. So, are we measuring the pressure in a single bronchiole? If we were measuring in a single bronchiole, how would it be? Very high. But how many terminal bronchioles do you have? A gajillion, right? It might not be easy to drink a shake through a coffee stirrer, but if you had 750 coffee stirrers all stuck together, might it be a little easier to get that shake to flow through it? Yeah, so it's the overall number. We have a massive number of them. And so the massive number of them collectively have a very low pressure. One single one would have a high pressure, but so many, when we're talking about gajillions of them, they're going to be very low pressure. Notice here we have one trachea with a large bore, but it's just a single one. So it has a fair amount of resistance. Notice we go to the secondary and the tertiary, and as we're going through those, the resistance goes up. Because what's happening to the diameter of our bronchi? They're getting smaller. And as they get smaller and smaller, from 1 to 2 to 5 and so on, they get smaller and smaller. However, once we get to about the medium-sized bronchi, even though their volumes are still getting smaller, what's happening to the numbers of them? They're increasing dramatically. And as the numbers increase dramatically, we see a drop in the overall resistance. So, with the medium-sized bronchi, there are few of them, and they're small in diameter, and that is where they have the highest resistance. Remember also we talked about those medium-sized bronchi. By we've gotten to the medium-sized, do they have complete cartilage rings around them? No, they're regular plates. And what else do they have? Large amount of smooth muscle, which is really good for what? contracting or dilating, changing the diameter. So diameter changes here at the medium bronchi. Can they have a huge impact on the flow of the air into and out of our lungs? Yeah, absolutely. So absolutely, we're going to have a huge effect by being able to change the diameter of those medium-sized bronchi with things like our sympathetic and our parasympathetic nervous system to cause those to contract and to dilate. All right. So, again, the goal is to maintain that flow, but there are things that can affect the resistance. As we've talked about, changing the diameters of the medium-sized bronchi, but also our parasympathetic constricts the bronchioles as well. They're tiny, but still there's many of them, so if we have a constriction in those, that can affect air. As we talked about in 430, those poisonous mushrooms that you can find wandering in the fields up in Tahoe, right? They stimulate a parasympathetic response. They're parasympathetic agonists. So they stimulate the parasympathetic nervous system. Your heart rate decreases. Your blood pressure drops. Your airways constrict. Your pupils constrict. You become all sweaty from eating the wrong mushroom. Conversely, right, if you have eaten that wild mushroom and shoot yourself with a shot of adrenaline, that is going to dilate all the bronchioles, increasing airflow, reducing the resistance. This is very useful for anaphylaxis, as we talked about. Anaphylaxis can cause a thickening of the mucous membranes of our airways, making it hard to get that air through. So if we can get the airways to dilate, then that means that even though the mucous membrane is thickening, we can still get air in there so that those individuals can survive. All right? Questions on that? All righty. The last concept we need to talk about in lecture today is to talk in terms of the respiratory volumes and capacities. Since I'm going to need the board anyway, I'll just do this here. In ancient times, and by ancient times I mean when I was in graduate school, we used a spirometer, but a spirometer was basically two buckets. You would take bucket A, and you would fill it with water. You would take bucket B and submerge it. Fill it with water and submerge it in bucket A. And it would have gradations on it. And then you would take an incredibly technical piece of equipment known as a garden hose. And you would connect this hose into the buckets. You would then take a normal breath in, right, from the air, not from the hose. You don't want to breathe in from the hose. Breathe in from the air and take a normal breath out into the hose. And as you did that, of course, air would enter into this. That would cause the bucket to go up. You would count how far up it went, and that would tell you how much air you blew out. All right? Or you could take a maximal exhalation. However, would this be do a good job of measuring how much air you inhaled?
No.
No, not very well, absolutely. So again, incredibly sophisticated piece of device, but luckily for us, we have a much more sophisticated one. We have a mechanical spirometer, which can measure airflows, and will be able to measure your inflow and outflow. So we're going to use these spirometers. You're going to use it in class today, and we're going to talk about it right now in lecture, to measure our respiratory volumes and capacities. All right? Now, I am going to throw numbers at you as we go through this. However, I will tell you right now, the numbers are not important. Right? The numbers that I'm going to give you are the average for an adult male. And again, if we took these respiratory volumes and capacities of every single male in this class, would they all be the same?
No.
No, of course not, because there's so many factors that influence our respiratory volumes, our age, our body size, our gender, your physical conditioning. All sorts of other factors can influence it. So you are not to memorize these numbers, but you absolutely need to memorize their definitions and understand the calculations associated with them. Because I guarantee you with 100% certainty, there is going to be at least one essay question on this where I'm going to give you a bunch of numbers and give you a bunch of volumes and capacities, and you're going to have to calculate other ones. All right, so we can do the math. We'll use some generic numbers here, but understand the definitions and understand the equations, understand their relationships. That's the things that you need to know. All right? The last thing you need to know is that there are going to be 10 important volumes and capacities that we are going to identify. So I need the board. So, as we will go through briefly when we come back from this break after this and start the lab, as I mentioned, you're going to be setting up the spirometer, you're going to calibrate that spirometer, and once that is done, basically what you are going to do is holding that spirometer to your mouth with your nose closed, you are going to take 3 normal breaths. You are going to take a maximal inhalation, a maximal exhalation, and then 3 normal breaths. All right, you'll sit there. And then 3 normal breaths again. And when you do that, after you're done, your spirometer is going to look a little something like this. And in the interest of space, I'm just going to put 2 at the beginning. Maximal inhalation, a maximal exhalation, and then 2 more normal breaths. And your spirometer is going to look a little something like that. All right? From this, we can then identify and describe our 10 important volumes and capacities. The first of these, and I'll stick with black for this one because it's a good basic one, is what is known as your tidal volume. Your tidal volume is the amount of air you breathe in and out in a normal resting breath. All right, so while you're sitting here calmly, just doing your normal breathing in and out, you are moving a tidal volume of air into and out of your lungs. Now, after you were to take a normal inhalation, is your lungs filled to capacity? No. Is there space for you to be able to take in more air above that normal resting breath if you needed to? Yeah, absolutely. And so we have a fancy name for that. The fancy name for that, the amount of air that you could bring in above what you would normally take in from a resting breath. So this is, we could think of it as the extra space for air above the resting breath. We call this the inspiratory reserve volume. taken a normal inhalation, you actually have more room in your lungs if you needed to take more air in. And that extra amount of air we would call the inspiratory reserve volume. All right? Now, when you take a normal exhalation, is your lungs completely empty?
No.
No. So after you've taken a normal exhalation and your hand suddenly caught on fire, would you have some extra air in your lungs to blow it out?
Yes.
Yeah. And that is because after our normal exhalation, there is still an additional amount, oops, my line is off. There is still an additional amount of air that we have the ability to move out of our lungs. And this is our expiratory reserve volume. This is the amount of extra air you can move out after a normal breath. When you take that forced exhalation, when you expel that expiratory reserve volume, is your lungs empty then?
No.
No. If I took a steamroller, might I be able to squeeze some extra air out of your lungs?
Yes.
Yeah. Right? Because again, when we breathe out, even when we breathe out as much as we possibly can, do we want to remove all the air so that there's a vacuum inside of our lungs?
No.
No. What would happen to our lungs if we made a vacuum in there?
Collapse.
It would collapse, and we don't want that to happen. So even after we've taken as much air out of our lungs as we can, there's still some air in the lungs. And that air that remains in the lungs is what we call the residual volume. So the residual volume is the amount of air in the lungs that cannot be removed, that stay in the lungs unless you have a steamroller. All right? Questions on that? All right, let's throw some meaningless numbers at these. As I mentioned, our tidal volume is the amount of resting air moved into and out of your lungs during normal resting breath. And it's about half of a liter. I'll write these numbers on the board because it'll be convenient for us later, not because they're important. We have our inspiratory reserve volume, the amount of extra space we have in our lungs to fill with air if we need to, and that's a little over 3 liters.
That's a lot.
After we've taken a normal breath, there is extra air we can move out, and that is our expiratory reserve volume, and it's about 1,200 milliliters. And even when we force that air out, there's still a little bit of air left inside, and our residual volume, which is also about 1,200 milliliters. Sit there.
Thank you.
Do those four make sense? Because if they don't, it's about to get a whole lot worse. All right. Let's start. Those are our four important volumes we need. Let's start talking about some of our capacities. Right? One of the simplest capacities is what is known as, here, let's use purple for this enough. What is known as our vital capacity. Our vital capacity is the total amount of air we can move into and out of our lungs. How do you think you would calculate your vital capacity?
Add everything except for residual volume.
Excellent. You would have the amount you normally move, your tidal volume. To that, you would add your inspiratory reserve volume, the amount of extra air you could bring in, and the amount of extra air you could move out. And if we were to do that with our typical numbers, what would that value equal? How much? One more time. There you go. 4,800 milliliters. And when you're doing your spirometer exercise, how might you calculate that or measure that on our graph?
Take the highest and lowest points.
Yeah. You would go from the highest point all the way to the lowest point, and that would be your vital capacity. All right. Questions on that? Now, vital capacity is the total amount of air we can move into and out of our lungs. But is that our total lung capacity?
No.
No. Our total lung capacity would be the total amount of air in the lungs, or capable to get into the lungs. And how would we calculate our total lung capacity?
Add everything.
You'd add all of them, exactly. You'd add our tidal volume plus our inspiratory reserve volume plus our expiratory reserve volume plus our residual volume. Or if we were lazy and we knew it, couldn't we also just take our vital capacity plus our reserve volume? Yeah. And that might also make it easier for us to do our calculation. Because 4,800 plus 1,200 is what? 6,000 milliliters. 6 liters. 3 2-liter bottles. Right? Back in ancient times, and by ancient times I mean when I was in middle school, there was this wonderful elixir by the name of Purple Passion. Right? Any of you heard of it before? Doesn't surprise me, they discontinued it after kids started going blind. Right? Basically, Purple Passion was grape juice and Everclear. And you'd be able to get it in this wonderful 2-liter bottle that you would sit and try to drink during the night, and after you got completely sick from that, you throw up, and the pink grape juice that was in it, or soda that was in it, would make this absolutely multicolored vomit when it came out. It was truly spectacular. So if you think about how, because again, in middle school, you can't buy it as easily, so you have to smuggle it out. So you've got 3 of those 2-liter bottles under your sweatshirt, trying to sneak out of the grocery store. That's what your lung capacity is. Those 3 2-liter bottles that you're smuggling under your sweatshirt. That's the total amount of air that you can stick in there. All right? Questions on that? Excellent, but there are a couple other useful values we need to identify. The first of these, and we'll go with blue, is what is known as, where am I going to stick this? I'll stick it right here. Is what is known as the inspiratory capacity. This is the total amount of air that can be inhaled. How would you calculate your inspiratory capacity? Yeah, there you go, exactly. It would be our tidal volume plus our inspiratory reserve volume. And taking our shoes and socks off to do some quick math, what would that be? 3,600. And if we wanted to measure this on our graph, how would we do that?
Bottom of tidal volume to top of inspired.
Bingo. From the bottom of our tidal volume all the way up to the top of our max inhalation. Finally, we have the functional reserve capacity. This functional reserve capacity is the amount of air that stays in the lungs and therefore can be used for gas exchange, which is why it's functional, after a normal exhalation. And how do you think you would calculate the functional reserve capacity? Say that again? Exactly. This would be our expiratory reserve volume, the amount of air that we can move out after normal breath, and the amount of air we can't move out, our residual volume. And if we were to do the simple math here, what does that work out to? 2,400. Inspiratory capacity. What did we say the definition of that was again? Yeah, how much air you can bring into your lungs, right? And of course that is not just after a normal breath, but including the normal breath. So that's why you calculate it with the tidal volume, which you normally bring in, plus your inspiratory reserve volume, everything extra you can bring in. And again, if we do the simple math on that, it worked out to about 3,600. And again, do you need to memorize this number? Do you need to memorize this equation?
Yes.
Absolutely. Our functional residual volume, oh, I always get that wrong. It is residual volume, sorry. I knew as soon as I was writing it that I couldn't remember which one it was. The functional residual capacity, how do we define that?
Amount of air that stays in your lungs for gas.
Yeah, the amount of air that stays in our lungs after a normal exhalation, right, a tidal exhalation. And yes, because it stays in the lungs, that means it can still participate in gas exchange, which is why it's functional. So that functional residual capacity is the amount of air that can be expelled after a normal breath. We didn't draw that one. plus the, did I have it backwards then? Is it reserve? No, it is residual volume, okay. Don't know why I had that. Residual volume plus the expiratory reserve volume. We have our vital capacity. How do we define that?
Total air we can move in and out of lungs.
Total amount of air we can move into and out of the lungs. And how do we calculate it?
Everything but residual volume.
Yeah, add the tidal volume, expiratory reserve, and expiratory reserve to them. And then you add them all together, and we get our total lung capacity. And there you go. Questions on that? Yeah.
So is this similar to the ECG where it's measuring change versus the actual
Yes, you
amount?
are measuring the physical movement of air into and out of the lungs. So yes, this is absolutely a change. Great question. It wasn't the one I was expecting.
Listen to-
What?
listen to-
Yeah, didn't I say 10 volumes and capacities? And that is because we have to come back to this tidal volume. When we come back to this tidal volume, this is the total amount of air moving into and out of our body. And yet, does all of this air that we bring in from that normal resting breath necessarily make it all the way down to the alveoli to participate in gas exchange? No. Some of it might only get as far as the nasal cavity, right? Some may get as far as the larynx. Some could get to a primary bronchi. Heck, some could be at a terminal bronchiole where it can see gas exchange taking place, but doesn't get to actually participate in it, right? So this tidal volume is actually broken into two volumes. Those two volumes of that tidal volume include our dead space volume, the dead space volume is the amount of air that fills the conducting zone. Is it important? Absolutely. It helps to keep the airways open. It helps to, in the filtering and all of that other processing, but it doesn't get to participate in gas exchange. The part of the tidal volume that gets to participate in gas exchange we call the functional volume. Excellent. And of course, how would you calculate these? Tidal volume equals the dead space volume plus the functional volume. So if I gave you two of those, could you figure out the third? Yeah, absolutely. If I told you the tidal volume was 1,000 and the functional volume was 100, then what would the dead space volume be?
900.
900, right? So know how to use these equations. Now, again, I'm not holding you for these numbers, but I do want to point something out. Notice that, again, the average dead space volume is about 150 milliliters, and that means the functional is about 350 milliliters. So every time you take a new breath, you're bringing in half a liter of air, and only about 350 milliliters of that get to the alveoli for gas exchange. And isn't the lungs filled up with air already? Right? You already have that's not a comma. 2,400 milliliters in there. So you're barely adding 15% to that. So you're just mixing a small amount with what's already there, which will be significant when we get around to our partial pressures and talking about that. All right? I've done an amazing job of doing this on the board. Your book's got the great table that does a good job of both defining these for us and also giving us averages. But again, the numbers aren't what's important. What's important is the equations. So do not memorize these numbers. Right? I guess you can know the magnitude. It's probably good to know that you're taking in, 500 milliliters versus 5 liters of air with a normal resting breath, but hopefully that's obvious. 5 liters would be a lot to take in. But again, I don't care about the averages, I care about the equations. And you've got the pretty chart also. There's it with the words. Here's it with the pretty chart. That shows all of those the same way that we have talked about it today, drew in all of those. And again, don't worry about the numbers, know the definitions, know the relationships. Last thing I want to say before we're done with lecture is that remember there are also non-respiratory movements of air. Obviously speech, like I'm doing right now, is a non-respiratory movement of air. But there are plenty of other ones as well. Cough, sneeze, crying, laughing, hiccups, yawing. All of these are examples of non-respiratory movements of air as well.
Do we need to know them in detail?
The cause of hiccups is basically a disruption. So your phrenic nerve, as we learned in 430, is what primarily controls your diaphragm. And what happens is the rhythm of the fibers of the phrenic nerve can come out of sync with each other. And so what happens is different parts of the diaphragm are contracting at different times, and that disrupts your normal breathing pattern. So doing things like trying to take exaggerated breaths where you control the muscles and try to control it, and you can resync it that way. The whole swallowing water upside down and all that stuff, really, again, all you're trying to do with that is you're trying to make conscious movements of those muscles to try to resync them. However, what actually works, one of the things that works the best, and is my daughter's favorite, is to take a spoonful of sugar. Because your taste sensation, especially the taste sensation for sweet, follows a similar pathway as the phrenic nerve. And so if you take a spoonful of sugar, the large sweet signal that is sent to your brain can help to resync the activation of the phrenic nerve to reset your diaphragm. I mean, it's all of those things. The drinking the water upside down, the holding your breath, all of those things. Basically, what you're doing is you are trying to voluntarily, because these are skeletal muscles, change the firing patterns to disrupt that asynchrony. So yeah, I mean, all those things have the potential to work. Does holding your breath every single time you get the hiccups work? No. And so I mean, it's all you're doing is, I mean, probably the easiest way, rather than drinking the water, rather than holding your breath, is what you do is you just breathe normal and relaxed. And what happens is every time you hiccup, change the pattern of your breath. So if you were inhaling when you hiccup, instantly start exhaling, right? If you were exhaling as you hiccup, instantly start inhaling. And so if you sit there and kind of, again, reestablish the control, that's usually the most effective way of doing it. But those other things can be effective as well. But they're not as much fun as a spoonful of sugar. Yes?
Talk about taste with the phrenic nerve. Is that why spicy foods can cause people to hiccup?
Sure. That's
activation
probably a
of
good
the-
point. Yeah, that would be, I hadn't thought of it that way, but that makes a lot of sense. Yep.
I have a question.
Yes.
How come this book doesn't talk about the DSB functional volume and the dead space? I mean, how would you measure it on that?
So, okay, so again, so let's think about this. Technically, can you, when we're using the spirometers, calculate the residual volume?
No, I mean the.
I know, but we're working to that. Technically, what I've got Dre here hooked up to the spirometer, can I actually measure her residual volume?
Yeah.
Sure, I just need a steamroller to roll her over after she's taken a maximal exhalation to force all that extra air out. Now, she might not enjoy that experience, and it's an experiment we can only try once,
Yep.
so it's not very valid, right? So this is something that we typically can't calculate. So we're gonna use an estimate number, right, of like 1 liter or something like that. There are ways, without rolling somebody over a steamroller, by buoyancy, checking the buoyancy, there are some ways of doing things like that. But it isn't something we can measure with a spirometer, and the exact same thing is true for these two. These two cannot be measured with a spirometer as well. However, like I said, on the exam, if I gave you the tidal volume and I gave you the dead space volume, could you calculate the functional volume?
Yes.
Yeah, the same way that if I gave you the expiratory capacity, if I said the expiratory capacity was 4,000, and I told you that the tidal volume was 1,000, could you calculate the inspiratory reserve volume? Yeah, exactly, 3,000. And that's exactly what I'm going to do on this exam. I will give you some of these values, and I will ask you for the definition and to calculate some of these others. So I may give you these two and ask you to identify and define and calculate the inspiratory capacity. You'd have to do that. So yes, I'd have to give you some of those numbers to figure that out. Okay? But yeah, it can't be measured. It can't be measured on the spirometer. All right? Great question. Any others? Yes?
Did you say the definition for dead space volume again?
Dead space volume is the amount of air in a tidal breath that does not get to the alveoli to participate in gas exchange. So it basically stays in the conducting zone. Whereas the functional volume is the amount of the tidal volume that gets to the alveoli and gets to participate in gas exchange. All right. Any other questions? All right, let's go ahead and take our second break. We'll come back at 10:25.